Hi, everyone. My name is Matthew. I'm a software engineer, and I help build quantum computers. And I'm curious just to help calibrate, by a show of hands, who here is already excited about quantum computers? It's a mix. Who's like skeptical? OK, good. Are there any physicists here? Oh, good. We're safe. Cool. So this talk is about quantum computing, but it's also about you, all of you. There's probably today less than 1,000 people in the world who know how to program a quantum computer to do useful, novel work. They're mostly theoretical physicists. In many ways, right now in quantum computing, it's like the 40s in classical computing. You have like John von Neumann helping develop the first general purpose digital computer. But what will unlock the potential of quantum computers is when it becomes the province of more than just theorists, which means people like you. There's only one downside, and if you get your news from the internet, you may be already familiar with this. I certainly am. The quantum computing hype machine is going into overdrive, and it all started 2 months ago when Google announced quantum supremacy. Okay? They published a paper showing that they performed an experiment in minutes that would take the world's most powerful supercomputer at Oak Ridge National Labs 10,000 years to calculate. IBM, who built the computer, was like, not so fast, it'll only take a few days. But still, this was a major watershed moment when a quantum computer could do something way faster than a huge, really the most powerful supercomputer in existence. The physicist John Preskill calls this quantum supremacy. Google's computer couldn't be used to do generally useful work, right? Or run like arbitrary user programs at high quality. It was optimized to prove supremacy, but it's still exciting because many folks said it couldn't be done. Of course, once things got exciting, people started worrying about Bitcoin. There's kind of a dictum in the industry that like the way you'll know there's a really large quantum computer isn't that someone's going to publish a paper, but rather all the Bitcoin will mysteriously disappear. So celebrities started jumping on the bandwagon, saying all codes are crackable. If you're unfamiliar, in great American tradition, this gentleman is running for president. It's only a short step from all encryption being broken to reality itself not existing. And at that point, we might as well have a time machine. And of course, give the time machine to a quantum AI. I bet this is a question you have never before asked yourselves. But isn't asking new questions really the spirit of YOW? So we're somewhere on this classic chart. Right now, we're headed for the peak of inflated expectations, to be followed by the trough of disappointment, which is like a great place for a beer. In this talk, I hope to shield you from the hangover of disappointment, but also to help you understand why quantum computing is super exciting in spite of all this, how it works at a high level, how it will affect your life, and how you could get involved, as Michelle said, if you do find me convincing. So how do we get here? We'll enter our quantum time machine and travel 40 years into the past. Here's handsome bongo player Richard Feynman, Nobel Prize-winning theoretical physicist. He first proposed quantum computers as a thought experiment in 1981. Feynman had gotten his start as a young member of the Manhattan Project, developing nuclear weapons and blowing things up to see what would happen, which is like the American way. Eventually, people realized this was bad. So as early supercomputer technology came online, we were able to start simulating particle interactions virtually. Take nuclear fission. A single neutron collides with an atom, destabilizing the nucleus and causing a split. It's just a handful of particles. But in Feynman's day, back at Oak Ridge again, they had one of these IBM supercomputers, and you need way more atoms to build one of these, right? Quadrillions of atoms, 1 million atoms probably for a transistor. So you can imagine it adds up, even if you don't count like the interfaces in that cool chair and stuff. So Feynman asked the question, why do we need so many atoms? If a handful of atoms can simulate themselves just fine, why do we need 26 orders of magnitude more atoms to simulate them? To answer this question, close your eyes and imagine an atom, okay? I don't see a lot of closed eyes, but maybe you're really good at visualization, being computer scientists, okay? So you probably pictured something like this, because there's no physicists here. This is the planetary model of the atom, right? This is what I learned in high school. There was like hand waving saying it's not really this, but the Bohr model is sort of what we think of. Electrons are like little moons orbiting around some central planet. Okay, I can't help but picture this, and probably you can't either, should you have occasion to imagine an atom. In reality, we know this is totally wrong. They're not little moons. I mean, not in the sense they're not made of rock, but they're really not even little balls. You should think of electrons as waves of probability that can be just about anywhere. Electrons belonging to me could be like far, far away across this room, theoretically. Though most of the time, they're pretty close to the nucleus. This is one of the first ever composite images of the hydrogen atom. And what you're seeing basically is a cloud of probability everywhere they saw the electron. And you'll notice there's some major orbitals where it's more likely to be found. But actually, the glowing extends off into space. The electron might be anywhere. We don't know where the electrons are until we observe them from outside, collapsing their wave nature and seeing them as particles. So now we can start to answer Feynman's question. You might have thought, intuitively, nature only needed a few hundred numbers to describe a few hundred electrons, like you're picturing little moons or beach balls that have X, Y, and Z coordinates like a game or something. But we actually need exponentially more numbers. If you leave aside quantum physics, because it's really hard, you can imagine a particle could be red or blue. In real life, maybe this is like spin on an electron or something. There are two ways to color that one particle. But if we have 100 particles, there are 2 to the 100 different ways to color them. So to make this like concrete, here's caffeine, a molecule we're all familiar with, the most essential ingredient in enterprise software. It's got like 150 electrons, okay? Technically, each electron can occupy countably infinite orbitals, as I was saying, like somewhere way out there, but let's keep it simple. It's mostly in your coffee cup. To get to chemical accuracy, meaning to know things about the molecule that would predict its behavior and properties a priori, we need like 2 to the 150 bytes of RAM. Doesn't look that big as 4 numbers. So just to like put it in perspective, it's like order of magnitude a computer the size of 10 moons, like the moon out there, to simulate caffeine. Or just a couple hundred quantum bits. And this was Feynman's insight. If we could manipulate some quantum system directly, then we could easily simulate molecules and interactions without actually performing them. So you may naturally ask, what is a quantum bit? And to answer that, we'll detour briefly into quantum mechanics. Without the quantum physics, because again, it's hard. I'm not a physicist. I am aware that this talk is being taped, so if you happen to be looking at this on YouTube years later and you're studying for an exam and this somehow came up, like, stop now. It's really for these people, not for you. Okay, so to situate quantum mechanics, picture like a dependency tree of science, okay? So neuropsychology answers the question of like, why is this guy on stage? And my consciousness runs on cells, presumably, which are biological in nature, which runs on chemistry, which runs on physics, which runs on math, which you could say runs on philosophy, epistemology, et cetera. Quantum mechanics basically fits right between physics and math. Scott Aaronson, whose book and blog I highly recommend, has a great phrase. Quantum mechanics is the operating system that the application of quantum physics runs on. It's just math. And actually, we could have derived quantum mechanics hundreds of years ago if we had a need. It was developed through the study of quantum physics, but there's nothing inherently physicsy about it, okay? It's just a generalization of the probability theory we use every day. So as a brief refresher, probabilities are real events that sum to 1, right? Mathematically, we call this the one norm. There's one of the many ways of defining the size of a vector. So we can say things like there's 10% chance of smoky skies here in Brisbane, and that means 90% of the time tomorrow there'll be like clear skies, right? This is like a weather forecast. We're used to this. Quantum mechanics asks the question mathematically, what if we choose a different vector norm? The 2 norm is also known as the Euclidean norm, which you may remember from high school. And so the question is just, what if we made a probability theory that's like everyday probability theory, but based on the 2 norm instead of the 1 norm? And basically what results is quantum mechanics. Instead of merely real probabilities, we now have complex amplitudes that can be negative or positive, just like a wave has a crest and a trough. To get the probability, we just square the amplitude. So to make this concrete, with a regular traditional bit, the bits we use every day, we're either in a 0 state or a 1 state. It's like a light switch, a vector pointing up or down. Don't mind this fancy notation for writing vectors. It's just for like any physicists who like ignored the plea to like stop watching. Okay, a quantum bit or qubit can be somewhere in between 0 or 1, a superposition between these states because it's probabilistic. In this illustration, if we were to measure a qubit in this state 1,000 times, 750 times we'd see a 1, 250 times we'd see a 0, because our state vector is pointing like 75% of the way to 1. When we measure the qubit, like looking at that electron, we collapse the wave, and we always only see a 0 or 1. Just like how in the regular world, if we say there's a 20% of chance of rain, we either see rain or we don't. Like waves, the amplitudes of multiple entangled qubits, meaning part of the same quantum system, can interfere constructively or destructively. And this is where the power of quantum computers comes from. If you're a fan of the many worlds interpretation of quantum physics, like David Deutsch, you can even say parallel universes are interfering with each other to calculate the answer. Here's like kind of a better illustration. Did anyone do this as a kid? I did, right? This is like super fun. What Calvin is doing here is going back and forth in the bathtub, synchronizing his body with the water till the wave gets bigger and bigger and bigger. This is constructive interference, and then whoosh, a huge one. I think I actually did this after reading this comic as like a 7-year-old or something. So this is basically what a quantum computer does, okay? We constructively interfere our probability waves such that the right answer emerges from a probability distribution after running a calculation like 1,000 or 1,000,000 times, depending on how much statistical significance we have. And we see the right answer as a little peak, just like this. So the two tools we now have from quantum mechanics are superposition and entanglement, which lets us create interference. So you might say, great, I've got qubits. Are they going to be useful? And to answer this question, we'll take a brief detour into computer science. How many folks here formally studied computer science? It's like a mix? Cool. So we'll kind of get everyone on the same page. You probably are familiar with complexity classes, even if you haven't formally studied it. But to briefly recap, it's a way of talking about how hard a problem is, okay? And some classes you may be familiar with or will sound familiar. P are the class of problems that are quickly solvable, like, is there water on this table? Yes, there is. Cool. NP are problems that are quickly checkable. So it includes the problems in P, but also has problems that are really hard to calculate but easy to verify. NP complete are like the hardest of these NP problems. So like Sudoku, which I saw a lot on the plane, is if I have a complete board, I can really easily verify that I did it correctly, but it's hard to fill out, basically a brute force search. This is a good NP problem. And the reason this is important is problems whose solutions scale exponentially rapidly become impossible to calculate, like the chemistry problems we were talking about earlier that require moons of RAM. It's not that we don't know how to solve those problems, it's that no one's going to build a computer like at the scale of the solar system. And in fact, eventually we run out of atoms in the universe to build the computer. There's like 100, maybe 1,000 other defined complexity classes. Because quantum computing is probabilistic, one of the useful ones is called bounded error quantum polynomial time, or BQP, meaning achieving a successful run most of the time in polynomial time. This relationship has been proven. EXP is like exponential classical complexity. Basically what this is saying is anything you can compute in quantum polynomial time, you can also compute in classical exponential time. Or to put it another way, quantum computers have at most an exponential advantage over classical computers. We don't actually know this, but we believe they're not going to be generally helpful for NP-complete problems. So there's like a class of problems that's really hard that remain hard. But there are a whole bunch of problems that are still really useful. So this is what scientists like Aronson think the relationship between complexity classes is. Obviously, if you can prove P equals NP, you get like $1 million as like prize money, but really you could make trillions of dollars because you would have godlike powers effectively. So you wouldn't probably tell them you had proved it, or you shouldn't anyway, if you're sitting on that proof. This is what we think, okay? BQP includes some of the problems in NP, all the problems in P, and some other problems too, okay? Not everything is exponential. There are some quantum computer algorithms that only provide like a quadratic speedup. So for example, Grover's method is quadratically faster at inverting cryptographic hashes than a classical brute force attack, but a hash function with 256 bits of classical security still has 128 bits of quantum security. So it's not really like a world-changing thing. So you might say, damn, I can't automate solving Sudoku with a quantum computer. What kinds of problems are these actually in BQP beyond Feynman's original idea? And to answer this, we'll fire up our quantum time machine again. I really need like a good sound effect for that, so if you have an idea, see me after the talk. Okay, so after Feynman, theorists started exploring the idea of what quantum computers could do, and it became clear quickly that Feynman's idea was great. If we could isolate qubits from the environment, we could do these simulation experiments. But it wasn't that well funded. There originally wasn't money in theoretical physics, so for about a decade it was only of interest to like kind of obscure researchers, a handful of pure theorists. All the money, at least in America, was going to like orbital laser weapons in the 80s, which is classic for us. And then in 1994, this guy, Peter Shor, discovered you could use a quantum computer to efficiently factor really large numbers. And suddenly folks were willing to invest millions of dollars into quantum computing research. So we all know factoring 21 is simple. We can do it in our heads, right? And the cool thing about this is we can easily verify. Like if I tell you 7 and 3 are the factors, you can verify it, right? Trivial for you to check. This is an NP problem. Factoring a really large number, like this guy that I can't even pronounce, is really hard not only in our heads, but also for a computer. You know this is hard even if you don't work in encryption. Some of our most powerful and commonly used public key algorithms rely on this being hard. Just to like put it in perspective, if you want to know, like, well, how hard is really hard? Take 2048-bit RSA, quadrillions of years to brute force this on my laptop, this laptop right here. I mean, quadrillions, again, such a large number. What is it really? We don't often think of quadrillions of things. It's like trillions of times the age of the universe, so basically unbreakable. Even on the supercomputer that Google was fighting against in their paper, it would take basically infinite time, billions of years. But the quantum resource requirements are only 2 times the number of bits in RSA. So if you had like 4,000 completely error-free qubits, which I'll talk about a little bit later, to crack your 2048 RSA algorithm, you could break it in minutes, okay? This is where people start getting excited. A year after Shor has his insight, in 1995, the very first quantum logic gate is run at NIST. Dave Wineland gets the Nobel Prize, and Chris Monroe, the lead author, spends 20 years researching the physics behind this particular technological approach, and then co-founds IonQ, the quantum computing startup I work for, in 2015 to commercialize this research. To recap our history lesson, in my lifetime, we went from a thought experiment originated over bongos to quantum supremacy, okay? This is not like cold fusion or space elevators or whatever, where you're like, it's always 20 years away, or like high-speed rail in America. This is like a lifetime, a human lifetime, okay? And it's accelerating. And over these 40 years, people have been developing and deepening our relationship to quantum computers. What can they actually do beyond encryption? I talked about simulating caffeine earlier, and why does this really matter? Chemistry is really hard. Take synthetic pharmaceuticals. I assume most people in this room have taken a pill at some point in their life. For many drugs that we rely on daily to save lives, to make lives better quality, less than 5% of the molecules in the pill are actually absorbed, because we don't know the optimal chemistry. Making a new drug involves basically spending billions of dollars on practically random walks in a wet lab till it's good enough to pass FDA approval, which I assume affects Australia. Literally, the state of the art, and I saw this at a conference that Samsung put on last month, is using a robot arm to do automated synthesis in a box. Basically, just automating brute force search, so like bored, grad students don't have to do it. It's still a very slow and time-consuming process. Being able to simulate chemistry without actually having to make those materials would have huge impacts for all sorts of problems, not just pharma. Imagine more efficient solar cells, or take the Haber-Bosch process, a better way to make fertilizer, okay? This completely changed agriculture like 100 years ago. 3% of all of our natural gas is burned this way. 3% of our carbon emissions is just making fertilizer. This is what sustains our current global population. By some accounts of the cells in your body, if you look at where the nitrogen came from, half of it is literally from this industrial process. You were made of this process. People are actively searching for more efficient solutions. Quantum computers could help. In general, because of the interference we talked about before, our intuition is that large combinatorial optimization problems are likely to have efficient quantum solutions. For example, optimizing logistics systems. Airbus invested in quantum computing for this reason. Or take finance. Citibank invested in a quantum software company. A bunch of other banks have too. Major banks often currently hedge their traders' positions using heuristic models. They're not perfect, they just work well enough. They believe that they could hedge their deal books perfectly using quantum computers, and that's why there's effectively a new space race. If they don't invest in figuring out these algorithms now, someday, when a sufficiently large quantum computer arrives, they'll get beat on every trade. And to illustrate this, this is a picture of the way trading used to be, a bunch of people shouting, it's kind of like the romantic idea of stockbroking, not very efficient. Only 1 in 20 stockbrokers successfully made the transition from the open outcry system to electronic trading. Totally different skill set, right? It's believed that quantum computing, and likely that quantum computing will be a similar phase transition for many industries. If you don't prepare now, even though you're not going to get literal ROI today, 5, 10, 15 years from now, as progress marches on, you will suddenly be in a state where if you weren't prepared, you will be outflanked by other folks doing more efficient stuff in your space. So how do we actually build a quantum computer, which is really the important part? David DiVincenzo in the 90s came up with 5 easy steps, easy to say anyway, right? It fits on one slide. First, you make a qubit, or you find one in natural environment. Any 2-state quantum system will do. Some are harder than others. Then you isolate a bunch of them from their environment, just long enough to do this quantum computation. You have to have some way to initialize them all to the same state, just like initializing a classical register. You have some sort of universal sets of gates, and then you have to measure each one individually at the end of your program. The reason this is so hard is why it took 20 years from the first logic gate being run in '95 to the last 4 or 5 years when people are actually building significant scale systems. Just for perspective, humans have come up with a lot of ways to do this. There's no one way to build a qubit yet. The jury's still out. There's 2 major ones, which are kind of the top categories here. Superconducting circuits using Josephson junctions. This is basically like little loops of wire cooled to nearly absolute zero, just a handful of millikelvin. This is what Google's doing, IBM, startup Rigetti, other folks. Or trapped ions. That's what we're doing at IonQ, Honeywell, AQT. Folks in Australia have actually a bunch of expertise in this area too. But there's a million other approaches. Diamond vacancies, quantum dots, photonic systems, neutral atoms. Since we work with trapped ions, that's what I'll describe to help ground this in reality. Start with the vacuum chamber, basically the size of a soccer ball, or I guess I should say a football. To get quantum effects, you need to isolate our quantum system from the environment. We want those qubits to be totally not in touch with anything but each other. So this vacuum is about 100 trillion times less pressure than the air we're breathing right now. Basically the best vacuum we know how to make currently. Even a single hydrogen atom evaporating off the inner surface of this chamber can mess with us. So you notice it's made of metal, and you might say, where's the hydrogen? Well, during the manufacturing process, hydrogen is trapped in the metal, and it slowly works its way out. Everything around us is evaporating all sorts of stuff. It doesn't really affect us at our scale, but at the quantum level, it really matters. Inside the chamber, we mount an ion trap, which is what you're seeing here. And to zoom in on that, it's a bit like a chip the size of your thumb. Very mature technology. It's been around since the 1950s. It powers all of our atomic clocks. Basically, it's a system for generating electromagnetic fields that allow you to hold charged atoms in place. Atoms, in our case, will be sitting right over that dark line in the middle, which is like a slot in the trap. And we're going to transition now from like photographs to keynote illustrations. So forgive my lack of fidelity here. Inside the chamber, there's a block of ytterbium-171, very heavy rare earth metal with 2 electrons in the outermost shell. We have a lot of it in the States because it's also used at NIST to make basically the world's most accurate atomic clocks. Step 1, we apply heat to start evaporating some ytterbium. A plume of hot ytterbium starts to form off this block. We zap it with an ionizing laser and strip off one of the outermost electrons. Now we've got hot, positively charged, heavy ytterbium floating by in our vacuum. As it floats along, we're going to zap it again with another laser to cool it. And this may sound counterintuitive because you think of lasers as like burning stuff or like shooting airplanes out of the sky, whatever. Laser cooling is basically shooting photons at something to make it slow down. So you can sort of think of it as like someone's trying to walk across a room and you're throwing rocks at them. They're going to probably be like, why are you doing that? But more importantly, they're going to slow down in the direction of travel. That's what we're doing here. Photons hit our atoms and slow them down. Okay? And now we have cool ytterbium, and it's cool enough and moving slowly enough. When I say cool, right, at the atomic level, it's not like you could put a thermometer in here and measure the temperature. We're talking literally the speed of these atoms, which is how we experience temperature, right, at much higher scales. the individual atoms line up like a string of pearls because we're holding them in place with all those electrons on that ion trap. So really, we're compressing using electric fields to hold these guys perfectly still, effectively absolute zero, because they're completely not moving. Now again, this is a room temperature computer, but the atoms themselves are at absolute zero. They're not moving. Each atom, each ion is a single qubit, and we manipulate their quantum state with lasers to make them do math, right? So we pew, pew, shoot them with lasers. You can shoot two at the same time to perform logical operations, like only flipping the one on the left if the one on the right is already flipped. At the very end, we energize the atoms with another laser. The ones that glow are ones, the ones that don't are zeros, okay? Actually, very simple. This is the simplest part. It almost is like a classical register, right? You can read the state just by looking at the atoms themselves. So this is all sort of abstracted, but I took a video earlier of 25 actual ions in one of our quantum computers. This is not perfectly focused, but what you're seeing here are 25 individual atoms floating in space. Zoomed in, obviously. This is not life size. Technically, you could see these with the naked eye if they were a different kind of atom. These atoms, we're energizing them with an ultraviolet laser. So if you looked at this, you would just get cataracts while you're looking at nothing. So instead, we're looking at them at basically a conventional, if high quality, CCD camera. We're shining them with a laser, which kicks that outermost electron into a higher energy level, falls back down, emitting a photon. That happens many times per second, causing this glow like a little ball. In the background static, that's really just photons bouncing around. This is basically how atomic clocks work, if you ever wondered. This part of the experiment is basically an atomic clock. You just have one atom, and you just choose how many photons per unit time is, like what a second is, and then you have a second, okay? Regardless of the technology you use, there are still challenges everywhere. It's very hard to isolate qubits from their environment. It's very hard to engineer a high-quality gate, even though we know the theory perfectly well. And there are errors in initialization and measurement, too. So what's the state of the art from a quality standpoint? In classical computing, right, zeros are free. When we initialize a for loop, we never worry, oh, what if I is not zero, right? It just happens. For quantum computing, not so. State preparation and measurement isn't perfect. We call this spam error. Right now, order of magnitude 1%. And the quantum logic gates that let us repeatedly update that state vector also have error. The gates have imperfect fidelity because engineering, focusing, and tuning lasers to make perfect quantum transitions is very hard. But there's a way out. Similar to classical error correction, it turns out it's possible to combine physical qubits, like those glowing ions we were looking at earlier, to create quantum logic operations with perfect fidelity, just like what we're used to with classical computing. We call these logical qubits. And depending on your fidelity and the error correction code for your technology, you might need hundreds or even millions of physical qubits to make one logical qubit. This is basically what's required to crack RSA, like those 4,000 logical qubits, which is probably millions or billions of physical qubits. How do we program a quantum computer? You can actually get a PhD in this, but there's not that much time here, so I'm just going to give you a taste of what makes it a little bit different. Okay? Right now, quantum programs are really circuits, a series of quantum logic gates that manipulate the state of your qubits. You measure at the end, because once you measure, you collapse all those superpositions, you collapse the wave, and you cannot get them back. This has all sorts of implications as programmers, like your loops have to be unrolled. But more importantly, it's way lower level than optimal. It's like writing FPGA code in logic gates instead of Verilog. People are working on quantum languages, but most of them are working in a vacuum because there aren't very many quantum computers. Mathematically, quantum computing is like a superset of classical computing. So you get all your friendly classical gates, ands and ors and so forth, but there's more. We have all these fun logic gates that you don't get in classical computing, like the really rad square root of naught, which doesn't even make sense, right, in the classical context. But once you have complex numbers, it actually does, right? All quantum logic gates, for the mathematicians in the room, are basically 2 to the n by 2 to the n unitary matrices that multiply our state vectors. So you can think of a quantum computer as like a really great linear algebra accelerator. If your parents were ever like, why are you studying linear algebra? So useless. Now you can say, got you, mom. It's the future. So just to take a couple examples to give you an idea of what we're talking about, here's a gate you don't see in regular computing, the Hadamard gate. It's kind of like a fun thing because quantum computing is developed more recently. everything is like named after people. You know, imagine like if the AND gate was like, you know, the Smith gate or something. That's kind of the world we're living in, because theorists were like claiming all this territory in the 80s when everyone was like, let's make orbital laser weapons, you know, instead. So the Hadamard gate puts any qubit set to 0 into a perfect superposition of 0 and 1. So if you have a single qubit and apply a Hadamard gate and you measure it 1,000 times, you'll see 500 zeros and 500 ones. Here's another one, the controlled NOT gate, which flips a given target qubit if and only if the control qubit is a 1. Okay? If we take 2 qubits and apply Hadamard gates to both after initializing them, what's going to happen? We end up with this nice distribution, 2 0, 0 1, 1 0, 1 1, right? If we imagine we apply a Hadamard gate to our first qubit and then apply a controlled NOT gate, such that we flip the second qubit if and only if the first qubit was a 1, we end up with this. We initialize everything to 0. Our first qubit is in a superposition of 0 and 1. Half the time it's a 1, so half the time the second qubit is flipped 2. And at the end of this experiment, before we measure, both of our qubits are entangled and both in a superposition. Thus, when we measure, if we ran this, let's say, 1,000 times, half the time they're both 0, half the time they're both 1. And with building blocks like this, we can build any circuit we want, including the one that breaks RSA. How fast are these operations? Superconducting gate times are measured in nanoseconds. Trapped ion qubit gate times are measured in microseconds. Quantum computers achieve supremacy not because the logic gates are super fast, but because wave interference is a powerful combinatorial computational tool. Okay? We don't need the fastest gates as long as we can do things that can't be done elsewhere. They're also actually quite efficient. I couldn't find numbers on Google's exact power draw, but similar systems use on the order of 25, 30 kilowatts, mostly for the dilution fridges, to cool their system to close to absolute 0. For comparison, the trapped ion systems I work on use like 4 or 5 kilowatts, okay, single-digit kilowatts. In minutes on their kilowatt system, they beat a 13 megawatt supercomputer, crunching for days in the best case. That's like 20,000 times or more as efficient. So it's not like, oh, we get all this awesome chemistry solving problems, but then we are using all of our energy on quantum computers, like with Bitcoin, right? It's actually quite nice for the future of high-powered computing. And it's not just making qubits that hard, there's other challenges. As I said before, we don't really have enough quantum algorithms. For years, we had too few computer scientists, right? And now we have even fewer quantum information scientists. Quantum mechanics could be taught at a younger age if we divorced it from the physics. We need interdisciplinarians. At IonQ, we're promoting the idea of algorithmic benchmarks, similar to how we benchmark GPUs, because it's kind of irrelevant if you have 1,000 qubits if you can't actually run a real program, right? And the reason for this, for example, is many of the superconducting systems are printed on chips where you have qubits connected to other qubits by wires. That's great, but it means you don't really have a register in the classical sense, right? If I have a 32-bit register, you know, on a computer that we use every day, I can run any operation between any bit that I want, any pair of bits. With a quantum computer, not necessarily. I have to use some of my bits to communicate, right, as intermediaries. And while it's true that developer experience is not great everywhere, or possibly anywhere, it's particularly bad for quantum computers, okay? I assume most of you don't write your programs in pure logic gates. Anyone who does, that would probably be a cool talk, but not actually how you want to spend your day, right? We need better abstractions and tools. There's only a few folks working with quantum computers that have like languages actually being developed. And having 70 years of classical computing to draw on is a mixed blessing, right? This is like a trade-off, because we can just pick and choose things that may already be like suboptimal from the classical computing realm. You're seeing this play out in actually business strategy today. You may remember the way Microsoft made PC hardware a commodity in the 90s, right? IBM was convinced the hardware is the important part, whatever software, and everyone was fighting to monopolize their layer of the stack and commoditize the other layers, right? People are already starting to do this for quantum computers, even though we don't have scaled up hardware that's useful, by way of example. So, what does the future hold? Hopefully you now have an understanding of the timeline of events thus far. This is sort of what we've covered today, 40 years ago, right? Feynman's thought experiment. And if we keep up our current pace of qubit scaling, we'll be building our first reasonably sized arrays of logical qubits within the next 5 or so years. Now again, handfuls of logical qubits, not breaking RSA, but on the path. And it's believed once we can make a few, it should be easy to keep making more, just as we saw in classical computing. So where are we on this path? Again, meaning like thousands of logical qubits. We're basically at quantum supremacy today, right? With another qubit or two, Google's supremacy experiment would be effectively impossible to simulate on any classical computer, including the world's biggest supercomputer. With not many more qubits than that, it will never be possible. Again, not because of mathematical reasons, but because there aren't enough particles in the universe to build the computer big enough to run the experiment. Okay, let that sink in. Even if we could build a universe-sized computer, which really probably not a good idea, even if you could not build it big enough, even with universal scale technology like that. So you might ask, well, okay, we're at the beginning of this important transition. What's the actual largest number ever factored using Shor's algorithm on an actual quantum computer? Does anyone know? You want to take a guess? No one wants to take a guess. OK, I'll tell you. It's not that shocking. Same number from before, 21. OK, so quantum computers definitely not coming from your Bitcoin anytime soon, leaving aside like the time-traveling ones from the future. I guess you always have to worry about that. But we talked about caffeine earlier. So you might say, well, how close are we on simulating molecules? Caffeine needs a couple hundred qubits. We're obviously not there yet. Where are we actually doing the simulations that Feynman dreamed of? Last year, my colleagues and I performed the very first simulation of the water molecule within experimental bounds. Now, just barely, right? This is still like a major watershed moment, the most complex molecule ever simulated on a quantum computer. But still, a very long way from actually changing how human pharmaceuticals are developed, how solar cells are developed, making new materials, and so forth. And as we saw earlier, many hard problems are still hard. A quantum computer is not a magic device for solving NP-hard problems and thereby giving us like godlike powers. But even this year, folks were estimating that quantum supremacy was a few years away. So this could all happen much faster than anyone thinks, even myself. And I work in the field. But if you'd asked me at this time 1 year ago when supremacy would occur, somebody did, and I was like, I don't know, 2 or 3 years, right? Seems like we're on the path. Google proved we're moving faster than that, okay? Even if we account for the trough of disappointment, it's likely to happen faster than anyone thinks. A huge part of what will accelerate this is access, okay? So if we think back to the 40s in classical computing, and the ENIAC was being developed, at that time, only scientists, right, and people working closely with them actually understood computers. 70 years later, we're in a world where not just all of us, but like an 8-year-old can make $1 million iPhone game, okay? Why did that happen? Because we went from a world where computers are the province of academics and like government researchers and the army and so forth to everybody. If quantum computers leave the lab, the feedback loop gets that much shorter. So here are 2 reasons to get excited. These are actually, in my opinion, not at all hypey, wired headlines from the last 2 months. If today you are an Azure customer, Microsoft announced third-party quantum computers will be available at Ignite like a month ago. And if you're an AWS customer, Amazon just announced their own competing quantum middleware service, last week at reInvent. These platforms aren't in private preview today, so it's not like you can literally open your laptop out there at the break and start using a quantum computer, but they will be soon available for anyone, including you, to help change the future of computing and thereby, perhaps human civilization. Thank you. I will take questions.
That was awesome.